I put up a slide here of some code. There's two separate programs on the left and on the right. So X is your data matrix that was your boss gave you. And you're just trying to learn a linear classifier for both or a linear regressive for both. And the question is, if you were to do this, if you were to run this code, would the question is the test error that comes out, is that an unbiased estimator of the true error? Or is there some bug in this code? And what is the change that you should make in order to change this code? So just think it's a little warm up for the first few minutes of class. Then we'll get into announcements and start the lecture. But I want you guys to think about this. Just wake up, get the cobwebs out, and think about this problem for a few minutes.
Can we talk about it, or should we just keep waiting?
Yeah, let's go through it. Anyone have anyone want to talk me through the first one?
Because we are using the mean of whole data, I guess it's not unbiased.
That's exactly correct. So we got our data set X, and now this step here is computing the mean on the whole entire data.
Are you trying to? Okay, maybe now it's working. You weren't pointing to any code.
Is it working now?
I don't think so.
Okay.
I see your cursor, but it's like under unbiased, not next to any code.
Ah, no, that's not what I want. How about now?
It's underneath error. Oh, now it seems, yeah. Okay, good.
Oh, weird. Wait, so but can you see my red? You can see my red writing though.
No, I can't.
No.
No.
This is fun. Okay, let's try this again.
Adventures in Zoom Academic Edition.
How about now? You see?
Now I can see some scribbles.
Yeah, I can
Okay.
see scribbles.
And now you saw it erased away?
Yeah.
Okay, thank you, thank you. Okay, so this first step where we're taking the mean, computing mu on the entire data set, that is touching both the training set and the test set, because when we go to, we do a random permutation and we make our training and test set, we're creating our training and test set after we've demeaned the data. And that's really not okay, because when we go and compute our Y train and X train, we compute our W and B, our offset and our W. Then when we have our Y test and X test, what's going on here is when you have our training error, it's computed on X train. But if we look at our test error, the X test is here, right? But this X test, part of these indices, because we took the mean up here, part of this X test bled into X here. And so because when we demean, part of this mean is using some of the entries of X test. And so when we went and computed W, that means W was affected by the test distribution in some way. And therefore, these are not independent. W is not statistically independent of X test because you demeaned from X train. And so on the right-hand data set, there is a separate, so on the right-hand panel, so no, and it's because this and this X test is bleeding into W through mu. Okay, so now on the left one, we've fixed this problem. So now we have that we compute our training and test set. We compute just the mean of the training set, and then we just subtract off the mean from the training set only. We compute our W, we compute our B. Everything's fine so far. This W and B, none of the X test is inside the W or B, so we're fine there. W is independent of the test. And then we get down to this step, and then we compute the training and test error. Does anyone see any problem in this code?
Should we be using the mean? Should we be using the means and standard deviation we got from the training set, not the test set, to standardize the test set?
That's exactly right. Right here, it's this step right here where we're demeaning the test set. But that doesn't make any sense, because if you and the see why this doesn't make any sense. Suppose your test set had just one data point in it. Then basically by demeaning it, you're making it 0. It just doesn't make any sense to do that. And what you should be doing is basically you want to use whatever your pipeline is for training. You want to use that same exact pipeline to pre-process the test set. So what should be happening here is using this X-train average to standardize the test set. You don't standardize it by its own average. You standardize it by X-train average. And now this makes sense, because now the test set and the training set have been normalized the same way, and they're still independent, because you're basically computing the the way that you are processing the test set just has to do with the training set, and the test has never got infected by the W, or is never bled into the W in this. W and B are completely independent of the test set, but you're still pre-processing them so that they're both demeaned in the same way. And this is good practice. So this is these are two very common mistakes. When I first came up with these problems, I sent them to some data scientists at Google and Intuit and some other tech companies, and I asked them to find the problems. only about it was something like, I think 3 out of the 5 people found them, but 2 out of the 5 missed them. So like it's really easy to write code and screw this up. Don't. Be very, very vigilant and careful, because again, if you show this to your advisor, or more likely, if you show it to your friend, they will laugh and mock you for having the test set bleed into your training set and not believe any of your results. So this program is how it should be done. This is sort of following best practices of how to do this, where I've created my training set, my validation set, and my test set. Because now what I want to do is I have some feature. This is doing a cross-validation sort of step that we'll get into today. So you'll understand sort of this piece in a moment. But the big thing here is to basically have a defined function that is a fit function. You give it X train, Y train, you fit a W and B to it, and then you have a different function that's just predict. And if all these things are encapsulated away, it's very easy.
Excuse
yes.
Me. We can't see the slide.
Of course you can't, because today they're just really making it easy for me. Okay, now you can see, right?
Yes.
Yeah.
Thank you. Yeah, sorry guys. I don't know. So anyways, this is basically I encourage you to look at this after class. Once we've gone through cross validation, this is sort of best principles for how you should be doing this. Essentially having a function that operates on the fit. So you're going to fit a W and B given a train and a test, and then a predict. And if everything's encapsulated away like this, it allows you to avoid some of these issues of contaminating the train with a test and things like this. But I encourage you to be vigilant.
And that's actually one reason why computer scientists can be particularly good at machine learning compared to people who come from other disciplines. You have all been trained, right? All of you who have computer science training have been trained. Don't reuse, don't copy paste. You should write functions and you should apply those functions, right? And this is one example of why you should do that. There are obviously uncountably more that you've seen before.
Yeah, and now just quick announcements. The grades for homework 0 have been published. We will accept regrade requests for a few days. I think I forget exactly how many days. I think it's on the website, but it is a limited amount. So go look at it now or after class. Don't hesitate because there is an expiration. Also, when submitting homework 1, please mark your answers in Gradescope. This is so when you upload your Gradescope, you have the ability to say oh, question 1.4 is on page 2, that sort of thing. You have no idea how much this speeds up the process of grading, and it's just a necessary thing to do. If you don't do it, we will take off points. So just do it, and it's easy for everyone. Thank you. I think that's it. Is there any other announcements, Jamie?
None that I can think of. We'll probably have you fill out a mid-course evaluation sometime soon, but we are still working out the details on that.
Great. Okay, then we'll jump right in. So last time we talked about, last 2 times, we talked about how we can control complexity through the complexity of our class. And so with the degree polynomials, this is like the degree of the polynomial. Like a 3-degree polynomial is less complex than a 7-degree polynomial, etc. And by increasing this highest degree or the degree of the polynomial, we're looking at less or more complicated function classes, and they can fit more, and how that affects the bias and variance. And at the last lecture we talked about something called ridge regression and regularization, which instead of adding or removing basis functions, regularization biases the learner towards a simpler solution in some sense. So in the sense of ridge regression, this was linear least squares plus an L2 penalty function. And so basically what this does is it encourages solutions to have a low L2 norm or low sort of length of that W vector. And this is because if there is any uncertainty, so like if there's say infinite solutions, if X is low rank, then W has an infinite number of solutions. It's not unique. And by putting in an L2 penalty, like ridge regression, it is essentially saying, all things being equal, please choose the W with the least norm. That's the intuition behind that. It also, and this extends to if X is not, maybe X is full rank, but it's ill-conditioned, meaning in some directions it's just not it's very flat. Saying if it's very flat in some directions, this can cause large sort of deviations based on small amounts of noise. And so adding that little regularization basically makes the result more repeatable. And it's more expected. The variance decreases, but you've incurred a little bit of bias. And so we saw that in the case of ridge regression, this parameter lambda, this amount of regularization that you're adding, this has a major effect on the bias and variance directly. I had some explicit examples of that, but I never told you how to choose lambda. And so that's what we're going to talk about for the next few lectures, or next few slides. And this is called the cross-validation or holdout set. So yeah, we have this training set, and we could use the test set to choose lambda, but you should never, ever, ever use the test set to choose hyperparameters, because the test set is really supposed to be just about evaluation. You really should think of your test set being in a lockbox until the very end. You've done all your training, you've picked all your hyperparameters, you've picked your lambda, and then the only time you look at your test set is right before you give the predictor back to your boss and say, here's my predictor. And your boss says, oh, but how good is it? And then you're like, oh, right, I should go run that on the test set. And then you go and run it on it, and you get a number back and you report it to him or her. And that is how you should think of the test set. It is not something that you tune hyperparameters on. So what do you do? One of the simplest ways to address this problem is to modify your training set a little bit. So consider the construction of a validation set. So let D, denote D, be your entire training set. This is all, if you have n examples of xi, yi pairs, D could be equal to xi, yi, I equals 1 to n, for instance. This is all your data. And now define dj as basically just the data set, which is x1, y1, dot, 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 xj minus 1, yj minus 1, and then xj plus 1, yj plus 1, dot, 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 x, and blah, blah, blah. Basically, it's just taking out the jth data point. That's it. And now define fd sub minus j as being the classifier, or sorry, the regression function, your least squares estimator with lasso, as the function that's trained on d minus j, d set minus j. So you're training not on the entire data set, but you're training on just the data set without the jth data point. And now what you're going to do is evaluate that estimator with the jth point taken out on the jth data point. So you trained on a data set that did not include the jth point, and you're evaluating that estimator on just the jth point that you did not train on. Okay, so these are completely independent. The data set you trained on and the data point, the jth data point that you evaluate on are independent. And immediately we get that this is an unbiased error of the true error of this estimator, because that jth data point was IID just like all the training set. And so if we take that one out and we evaluate FD set minus J on the jth data point, that's an unbiased estimate of the true error of how F sub D minus J behaves on future data. Of course, now the sort of obvious thing you would do next is compute basically repeat this over all of J, right? Because what we get is, if for each jth point we have this error, so FD sub minus J, this is the predictor that is trained on just the data set without the jth data point, evaluated on the jth data point and getting that error. And now we're just going to repeat this for all n data points and get an error. Okay, so this means because we have to compute a different F sub D set minus J for each J, this means we are training n different estimators or n different predictors F to compute this sum, because each one of these is trained on a different training set. And we're just sort of looping around all possible data sets of taking one point out of the data set, training classifier or training a predictor on that data set without that jth point, and evaluating on that jth point, and then summing that over all possible j equals 1 to n. And this is known as the leave one out cross-validation error. Now, as we were just discussing, if we just take the jth point out and we evaluate on the jth point, that is an unbiased estimate of F sub D set minus J. Okay. So it's almost like we're getting a look at what we would get, what we would if we trained on all the data set. It's almost as if we're training on that. But because this error is taking out the jth data point, it's it's not the same thing as training on all the data. It's close to it. And also, it's difficult to get a handle on the statistics of this quantity because there's so much dependency in it. But what we see is that it's essentially like almost unbiased, because each jth data point, it's an unbiased estimate, and like each sort of like any n minus 1 subset of your n data points is going to be pretty close to the full n. And so this leave one out cross-validation is actually a very interesting object of study. How does it behave relative to the true error, the true test error? And there's lots of theoretical works on this. It's actually much more tricky than you'd think. But it's a very, very good proxy for what the true error is. Now, and so what you could do is, of course, use this to train. You can use this to train to pick lambda. Sorry, folks. Okay. Yeah, so we'd use this to pick lambda. And the way we would do this is for each lambda, we would train n of these f d set minus j's, compute the leave one out cross-validation error. And so for each lambda, we compute the leave one out cross-validation error, and then we would choose the lambda that minimizes this cross-validation error. Okay, so we're only looking at the training set. We're never touching the test set, but because we're creating validation sets for each data point j that we take out. And then so we use this to compute the leave one out cross-validation error and choose our lambda to be the one that minimizes this leave one out cross-validation error. Are there any questions on that? Okay. So, of course, this gets really hard really quickly. If you have 100,000 data points, you have to compute 100,000 predictors, right? Because leave one out cross-validation means that you have to take a data point out, predict on, create a predictor that's trained on all 99,999 other examples, and do that 100,000 times. So even if it takes just a second to learn each one, it's going to take, about a day to do this leave one out cross-validation. It's just completely ridiculous to actually compute this thing. And of course, this has stopped mirroring. It's particularly bad today. I don't know why this has changed. And so it would take about a day, which is just not reasonable. And if you're familiar, we'll see later in the quarter where we talk about deep learning, where some of these models, modern, say, natural language processing models, or translation models, or modern vision systems, they actually, we measure training time in days, not in seconds, hours or days. And like some of these translation models actually take like a couple weeks to train. It's crazy. And so doing this is just totally not possible. And so in place of it, what we do is sometimes we do k-fold cross-validation, or even just one-fold cross-validation. And so what k-fold cross-validation is, instead of creating n different data sets of taking the jth data point out of the data set and calling that a new data set, we're just going to divide our data set into k equal size pieces. And then we're going to learn a classifier with basically on the data set D that does not include one of these k equal sized data sets. And so so if your data set was 100 and k was equal to 5, you would train on 80 data points and then evaluate on 20 data points, and you'd round robin. The k-fold cross-validation error is just summing over all possible partitions of that data, taking out the k, each one of these k partitions out and averaging over that. So this is very popular because now your computational cost, you're only computing k estimators, your k predictors, so that's good. But often even this is too much, say with like deep learning. And so often in practice, we'll do just a single validation set. So we'll break our training set up into 80%, 20%, and then train on the 80% and evaluate on the 20% and just call it a day. This also has the nice property that the statistics are easier to analyze. But if you can do k-fold cross-validation, it is sort of like the gold standard. Or one-fold cross-validation, or leave one out cross-validation is the gold standard, but k-fold cross-validation is the next best thing. Okay. So the benefits, of course, is just much faster. It's a little more pessimistically biased because now we're not training on n-1 data points. We're training on only k-1 over k times n data points. And so it's a little more biased or a little more pessimistic, but that's okay. So just to this is a very sort of simple sort of concept, but very important. When you're given a data set, because no one is ever going to give you a training and a test set. They're just going to give you a data set. And so you, as the responsible machine learning engineer, need to take this data set. The whole thing is your data set D. You need to take your data set. You need to break it up into a training and a test set yourself. Put the test set in a lockbox. Put it away. Never look at it. And just look at your training set. And now you're going to use model selection. And model selection is the practice of choosing any hyperparameters like lambda. This is like choosing the degree polynomial, or choosing the lambda for ridge regression, all these sort of things. You're gonna use the training set for that. And this is called model selection. And the way that you do this is you then further break your training set up into k-fold cross-validation. So k is equal to 3 here. where you train on, say, 2/3 and you evaluate on the last 1/3, and you try all possible permutations. And then you average all possible results. And then finally, once you've trained a model, once you've chosen what hyperparameters to do, you then choose that hyperparameter and you evaluate it on the test set. And never ever choose parameters based on the test set. You will not be trusted if you are found to be doing that. Is there any question on that, on the procedures? Okay. Self-test. Okay, let's take another few minutes to read this. You wish to build a predictor to predict the stock price of Zoom, our wonderful application here that everyone's using, despite its many flaws. And you want to do this given historical stock price data. So basically, you want to predict what it's going to be doing in June. Okay, you want to predict what this is going to be doing. And now your setup here is like, okay, I'm smart. I'm going to make a training and a test set because I took machine learning 101. And so what you did, you said, I'm going to all daily stock prices up to January 1st, 2020 as my training set, and then all data from January 2nd to April 13th as my test set. Okay. So I'm going to train on my training set and evaluate my test set and get some number back. What's wrong with this procedure? Is the number I get back on the test set any reasonable proxy for what I should be reasonable for how the stock is going to behave in June? Think about it for a minute, and I'll take some comments. All right, what's wrong with this picture? Someone.
Non-IID. Non-IID data.
That's right. That's right. The whole principle of creating a training and a test set in machine learning is that the training set has to be, number one rule of machine learning. The training.
Your writing isn't showing up, Kevin.
Oh, man. I am sorry, guys. I swear it was so much better. I remember even thinking to myself on Friday, like, wow, this has gotten so much better. This didn't drop out at all. Okay. The number one rule of machine learning is that the train and test set are drawn IID. That means they are drawn exactly the same way. They have the same statistics. They have the same mean, they have the same variance. Each data point in the training set is drawn exactly the same way as each point in the test set. And that is clearly not true here. Up until COVID, before COVID happened, January 1st, the Zoom stock price was doing okay. But of course, after COVID hit, the stock price has had a meteoric rise for a number of reasons. And so obviously the data that we see in the test set is not going to be independent and identically distributed according to the training set. This is extremely dependent sequence, and it's over time. If you add that timestamp to it, that really changes the data set quite a bit. And so these are just not IID data sets, and therefore, yeah, you need to do something else. You need to do a lot more modeling. We're not going to look at time series in this course, but there's a lot that you can do here. Let's take this example now. So say we have 10,000 dimensional data and n examples. Okay. Now, with very high dimensional data, often what we want to do is find some subset of the features. We want to narrow it down to a small number of features that are, say, interpretable or have all the meaning in them. Because of those 10,000, maybe the vast majority are completely uncorrelated with the thing we're trying to predict. And so maybe only like 50 of them are actually useful. And so what we're going to do, what this procedure does, is this coefficient. If you remember from Statistics 101, this is the correlation coefficient. This is just how correlated is the jth variable with the output, the y, the yi that you're trying to compute. And this number is in -1, 1. It's normalized. Well, not really. Actually, it's I would need to normalize by the yi's, but that's just a scaling factor, so it doesn't matter.
Whole day.
Sorry, Professor, there's a couple of hands in the chat.
Okay. Brendan.
Yeah, I just had a question about the previous slide. It seems to me that if you're allowed to train over samples of the stock over that entire time period, you're obviously going to do much better testing over that time period. But the point of training a model like this is to be able to predict the future, which is a period of time you can't sample from at all. So wouldn't it make sense to set aside future test data because you're trying to extrapolate into the future, and you're not going to be able to see how well you do that if your test data is more of an interpolation?
Yeah, so there's different ways of doing this. So this setup is clearly wrong, and yeah, you definitely want to be evaluating on that last data. But the problem really with this example is just that it's not IID. This is not a machine learning problem, and you should not be applying machine learning to this problem without more modeling assumptions. And so what you need to basically write down a model where where you can write down a model and then you can turn it into a machine learning problem. So one way of doing this is, let's say, let's just look at let's say X.
You're writing as a
Wow, really?
Yeah.
This is dropping every second.
It's just every time you change slides, it looks like. Yikes.
Okay. So let XTI be equal
Kevin,
to the.
One quick comment.
Yes.
It's not as good, but if you do use 2 different Zoom windows as opposed to screen sharing, I found it to be more robust, even though it doesn't give you some of the same functionality.
Yeah. I'm just worried that trying to go through the authentication on my iPad right now.
Sure, don't do it now, but just in the future if we have this same problem.
So if XTI is equal to the ith stock price at time t, then what you might say is that xt plus 1 I is equal to s equals 0 to k of xt minus k I, and then plus some noise, like epsilon t plus 1 I, where maybe this is Gaussian 0, 1. So if you believed your model, if you believed your data fit some model like this, now you can start reasoning about how what is independent, what's not independent, and you can start talking about long range dependencies versus short range dependencies. Oh, sorry, you want little coefficients here too, because an ARMA model. Minus s, sorry. And so basically, it's just saying that the next data point is a function of my k previous data points, a linear function of my k previous data points, plus some noise. And then what you would do is basically you would segment out your data. And under this model, if you believe this model is true, then training on something like doing this train test split is actually okay, because your data is assumed to be sort of fitting this ergodic model, and it doesn't matter where you look at your data. You should be able to fit this data. But like the point is that like if you're looking at time series data, you cannot really make a train and test split without really thinking harder about how your data came to be. What is the data generation process? Because you just can't argue that it's IID. And this comes to a bigger point of when someone gives you a data set, you have to think about like, is this IID? Is this actually, what do I mean when I want something to predict well in the future or to generalize well? And what that really means is that future data going to be IID to the data that I'm seeing right now? And if not, this is called the data set shift problem. And this is like one of the biggest problems in machine learning and how to study this. But these are kind of more advanced topics. Yeah,
Yeah, go ahead.
Is it related to this?
Yeah, I'm just curious. Like, let's say you're just given a data set. How do you check for IID? Like, what research would you do?
You can't. You cannot.
You can't.
You cannot determine whether a data set was drawn IID just by looking at it. That's critical. Okay. You cannot check for independence. You cannot check for any of these things. You can come up with a statistical test to reject the null hypothesis that something is independent, but you cannot check that, you cannot validate that a data set is independent or IID. That's impossible.
So let's say that you build a model and everything, and you have poor performance. I know in previous lectures you were saying that you should always intuitively consider bias or variance, but should you also consider that maybe this data set isn't IID?
Well, typically, if you had poor performance, if you're looking at a data set, the data set is in front of you. And so what I'm talking about here, the issues that I'm bringing up here is if there's some data set that if you're performing poorly, say like you break up your train and test and it's performing very poorly. And typically when you have a train and test split, you're going to randomize in some way. But like if you did everything right and you broke up your data set into a train and test, and then you got some model, and then when you evaluate this model in the wild, it performed way worse than your test error would predict. That means one of your assumptions was wrong, which would happen here. Basically, the underlying data generation process was never IID. And so you cannot know that by just looking at the data set. And so this is so critical to think about where your data is coming from. You cannot just be robots that, you can't just put in a code somewhere and run a script to say, yep, all the assumptions hold. You really have to think about where your data came from and if the underlying assumptions of machine learning hold. And this is this critical factor of IID that is so necessary for machine learning to work. And this is a very sort of deep thing. I mean, it's very simple. It's very easy to overlook, and it's overlooked all the time. But it's something that it just burns people over and over and over. And so there's something you actually have to think about. Where did your data come from? What does it mean to predict something in the future? Does that thing in the future, is that drawn according to the same distribution as the past?
Are these like questions you would ask your collaborators if they gave you a data set?
Yes. Okay. This is something that you have if you're doing collaborations with biologists or chemists or anything. These are questions that you have to ask your collaborators. So in medicine, this is a major issue. In comp bio, this happens all the time, where people will lots of comp bio data sets online are they're publicly available, which sounds great. But then after you've run some training procedure, you get some test set, and you get some good performance, and you go evaluate in the wild, and your thing doesn't work at all. Your prediction is just trash. And the reason why is because maybe those training samples were hand-picked by some doctor that were not actually like what patients are seeing in the clinic. They were sort of the very specialized and very sort of, they had particular attributes that bias the data set in a completely big way. This can also be, and so there's tons and tons of examples of this. Of in medicine, there was a huge issue of I forget what it was, but for a long time, New York City, you could buy corpses for really cheap, and they would basically these medical experts would try to get conclusions based on corpses, and most of these corpses were unclaimed. And so unclaimed corpses traditionally came from poor communities, and they just made all these conclusions from these corpses, not realizing that this data set that they were looking at was coming from from poor communities and very biased.
Mm-hmm.
The conclusions were just completely wrong, and it resulted in like cutting out people's thymus and things like this. It was completely ridiculous. And so this is like a case study in how the training set was not an IID representative set of the true data. Sorry if that was a bit vulgar.
It was not vulgar. It was surprising.
This is cadavers. They were cheap back then. Okay, Tim.
Yes.
Hand up.
Yeah. So is it never a good idea to prospectively evaluate machine learning models? Because I mean, that's kind of what I'm starting to take away from this. Or is it, or is that just like, is that a different idea from you're splitting the data? Or is it okay to build a model and then prospectively evaluate how it translates over time? Like, let's say it's like a biomedical predictor where you're trying to predict, mortality of patients. You want to know how that model is going to perform over time or degrade over time, right? Is that a different? You have to think about that differently.
Okay, so what you're talking about is how will it degrade over time. That is implicitly meaning that you're expecting the data over time to change. The data set the data that this predictor will be evaluated on, you're expecting that data to change over time, which is totally reasonable and very realistic. People's preferences change over time if you're doing recommendation systems. I mean, who could have possibly predicted the craze that is Tiger King, right? Like this is, preferences change, and you should expect that. And how to predict that is basically just to be aware of it. And so in practice, how these things, major infrastructure is set up in place to basically doing anomaly detection. As soon as you start seeing, if you're expecting X's to change in the future, there's lots of anomaly detection procedures that say like, well, look, I have my training distribution, I have all the X's I trained on, and now I'm seeing stuff evaluated in the wild of X's that are being evaluated on. As soon as I start to see a lot of X's that look nothing like the X's that I trained on, I declare a flag and I'm like, oh, something's wrong. Like I'm seeing X's that I never came close to training on. This data set is not the same distribution. This is called two-sample testing. This is done very frequently, exactly to address this problem. To be like, oh my gosh, the data set that I'm evaluating on is different from my training data set. I need to go and collect more data. That's basically what that flag is saying, is you need to update your distribution because the data you're evaluating is wrong. The more obvious one is just to do evaluating the generalization error. Just randomly sample some of my examples, see what that error is. Is that in line with what you were predicting the test error? That's a really clear signal as well to see if did performance drop. And if performance dropped, you need to collect more data and retrain.
Okay, so can I just get a quick clarification? So, like for instance, in biomedical informatics, there's a package that helps people build machine learning models for making clinical predictions right now. And there's an option when you're building your models to split the data in exactly the way here that's being set up. Older data first, you train on it, and then you test on future data. So are you saying that this widely used system is completely wrong and should never be done that way? Like, I just want to clarify, like they were doing it wrong.
No, I'm saying that model is making assumptions of how the underlying data was generated, and someone to use that function without understanding the underlying assumptions of what it is assuming is wrong.
Okay.
And this is a major problem that you might hear things like the automated statistician and tools like this that basically give people freedom to not know about statistics or not know.
Or the democratization of AI.
Yes.
Yeah.
All of these sort of things, which sound really great and are really great. The tools that are available to people to make predictions are just phenomenally easy to use and powerful. So like we want to get these tools into the hands of practitioners. However, when it comes to high stakes applications like medical applications and medical trials and things, you have to understand the underlying assumptions that go into these models that make them so easy to use. And without that, you are doomed to failure.
Yeah. Cool. Thank you.
Okay. All right. I know this is a long conversation, but like this is actually what I like to use lecture for, more the discussion of topics and answering these kind of questions. And because you can always just read the book, but having these sort of discussions about this is really what I value about lecture. So thank you for all the chatter and questions. Okay. So in this example, again, we have 10,000 dimensional data with n examples. And we want to pick some subset of 50 dimensions that have the highest correlation. We want to do some feature selection, essentially. We want to pick the 50 highest, the features that are most correlated with my yi, with my observable y. And then after picking the 50 features, we're then going to use cross-validation to train ridge regression with a regularization lambda. Okay, what was wrong with this procedure? It's related to what we talked about on the first slide. Anyone?
You have to do the step one only on the training data.
That's right. So a little more on that. Like, so basically, we can imagine this just being the training set. Like we're given 10,000 dimensional n examples, say like in the training set, right? It could even be the training set, but what you're getting at is, so we're picking our 50 indices, J, that have the highest score, and then we're performing cross-validation once we've picked these 50 features. And so this is not the split up of the training and validation is supposed to be basically some IID split. But as soon as if you pick your 50 from the training and the validation combined, you've bled some of by picking these 50, there is dependence now between that training and the validation set. And so what should have been doing, you shouldn't have cross-validation, but on each fold of that cross-validation, on each training fold of that cross-validation, you should have picked these 50 and then picked your lambda and then evaluated on the last fold, and then repeated this over and over. And so you should treat each fold of the cross-validation as if you're getting a fresh data set, and then evaluating the validation set. Because as soon as if you pick the 50 indices or you demean on the data set, you're introducing sort of this bias. And so what you always want to do is when you do these cross-validations, is when you look at the training part of the small subset of the validation, of the training and validation, when you look at that training, that has to be treated as if you're seeing it for the first time. Now, there's going to be a question that will come up, that always comes up, is, wait a second, if I pick 50 indices for k folds, I do k-fold cross-validation, I'm going to get k different sets of 50 indices, and they may not overlap, right? What do we do? Do we take the union of all these 50? So maybe it's going to end up with maybe at most, k times 50 indices. That could be possible. Are we going to take the intersection of these 50? Are we going to do some other procedure? All these are good answers. They're completely domain specific, and I don't have a good answer for you. Basically, you'll have to make that decision yourself. But basically, it's very possible that if you do this procedure on each fold, you're going to get 50 different indices, and how you combine those into one big set is a very good question, and we don't really have a great answer for that. Barraj, you have a question?
Yeah, so I was gonna ask, so like oftentimes when you're like, doing, like before training a model, you do like, some kind of like dimensionality reduction, right? So for instance, so like what you were saying to me, what you're telling me, I guess now that I'm thinking about it, is like if I'm doing dimensional reduction, say for a linear method, like PCA or something, so I should basically be doing PCA on the training set, and then given the PC vectors, I should be using that to reduce my test set, right? I shouldn't be doing all at the same time.
Exactly. Yes. Never do it on the entire data set. That is a common mistake that is responsible for lots of wrong answers out there. This is very easy to do, but it is wrong. And you could really be screwing yourself. Absolutely.
Yeah. So it sounds to me like a lot of like the nonlinear methods, you can't, you can't, I guess, use them to reduce new points. Normally they take the whole points and then, find some kind of like, use some cost function to like find some, local, some
No.
subspace.
It's just you're not looking at the test set. You can do anything you want with the training set. And so like, you're thinking of this as if that structure was real, because like, what are you doing when you're doing feature selection or trying to find a small subset of indices that are representing something real or some nonlinear structure or something like this? Your hypothesis is that this structure is real. There is this real structure to the data, so that structure should be present in both the training and the test set. So if I find it in the training set, if I apply that structure to the test set, it should still be there.
Right.
And so like it's yeah, and like it's a total. We'll get to unsupervised learning in the future. I'm going to talk about clustering and PCA and stuff. It is a total lie that you can't do cross validation on unsupervised learning techniques. You absolutely can. You should break your data set into a training and test and pick the number of clusters or the dimension based on how well that structure that you're learning is evaluated on this test set.
Right.
This is also a big problem. And this is a major problem in biology data. A lot of times you'll look at papers in Nature and Science, and they're just running t-SNE on the entire data set and like pretending that they found something real, where they could very realistically be just chasing noise.
Got you. Yeah. Okay. Thanks.
Because every t-SNE data plot will cluster, no matter if you're looking at random noise. Okay, we're going to move on now. And so just a recap, what if you're just going to do one split, which is honestly typically what we do. Often we are not doing k-fold cross-validation simply because it just takes a long time. Often we'll just do one-fold cross-validation, where when we get our data set, we'll split it up into a train, a validation set, and a test set, say 80%, 10%, 10%. And then we will choose some hypothesis class or model, like linear with some like random cosine features or polynomial. You'll put a projection to a high dimensional space by taking all polynomials of our data. Then we're going to perform least squares with some penalty. So like this lambda for ridge regression on the training set. We're going to choose the lambda based on the validation set, the performance on the validation set, whatever lambda minimizes the error in the validation set, because that's a representative of value of the true error for that lambda. And then we're going to choose our lambda, and potentially we're going to retrain on the entire training set, or just take that model that came out of that cross-validation step and then report the test error to our boss. And that is the solution. Okay. Any questions on this last on this section?
Teacher, I have a question.
Yeah.
In the bottom, like that, you use cross validation on the validation set to pick number of features. How would that work?
So that would be this sort of step. So I break my data set D up into train, val, test. So this is all the data set that I was given. And now what I'm going to do is for each lambda, and perhaps lambda and choosing, or sorting this this step, basically computing the correlation for every jth variable, and then just picking the top 50. You're going to do that on the training set, and then you're going to you're going to pick your top 50 on the training set. You're going to compute the lambda that's optimal for that for each value of lambda, and then for each value of lambda, you're going to get some error. So this is like error, and this is like lambda. You'll get some error function, and you're going to pick the value of lambda, validation error. You're going to pick the value of lambda that minimizes the error in the validation set, and like call that one, say lambda hat, and then you're going to, so the output of the validation set is some f hat of lambda hat, and then you're going to get in the test set, and you'll get out some value on the test set, and you'll get some number like 98% accurate.
Oh, okay. So for the feature selection or for choosing a number of features, we just use the data in our training set and determine the importance of the feature according to the correlation.
Yes, yeah, that would be a way of doing it, because that would be, you would train, you'd pick your top 50 indices that have this highest correlation just on the training set, and then you would pick your, for each value of lambda, you'd pick a different function that was trained on this and evaluate that on the validation set, and then you would get your test set. And the only reason why it's so critical to do that is because if you pick your top 50 features from the training and validation set, they've now bled into each other. And the fact that they've bled in, the validation set has partly bled into the training procedure. Then when you evaluate on the test set, and you take those top 50 indices, that's no longer going to be a representative, unbiased look at what that error is. And so picking based on that validation set is not going to be representative of picking based on like the true error of the test set.
Okay. Okay, thanks.
I think Brendan was next.
Yeah, my question was, after you use the validation set and before you check how your model is doing on the test set, do you usually fold the validation set back in? So then you're training on 90% and comparing against the 10. And then before you roll anything out, do you obviously use all 100% of your data? Or is there like some notion of never using things for the models?
Yes, that's a great question. So the question is, just to repeat it back to you, you're choosing hyperparameters based on just this 80%, or you're training on the 80% and then choosing the lambda based on how it performs on the 10% validation. And so once you've chosen your lambda, do I then combine my training and validation into one big data set and train all on that with that chosen value of lambda that I found during this procedure, and then evaluate that on the test set? Sometimes. And the reason why I say sometimes is because that seems intuitively very good, but parameters like lambda for the ridge regression, theoretically, if you go through the theoretical analysis, you'll find that the optimal value of lambda depends on the data set size. Which means that if you choose lambda based on the 80% and evaluate on the 10%, but then you choose that lambda and you use it on the 90% of the combined training and validation, that won't be the optimal lambda for that 90%. And it could even hurt you more than if you just used that value of lambda on that 80%. Not always, but sometimes that happens. So you just be careful. It really depends on the circumstances. So to be safe, no, you shouldn't do that. But like oftentimes that's totally okay and a good thing to do. And that's a judgment call that you're gonna have to make.
Cool, thanks.
Chethan?
Yeah. So actually, I have two questions now. So if you want to do it like right, would you just throw away that 10% and then just use a model you built on the 80% and test on the test set? Like if you want to do it like properly, and you don't want to bleed.
Yeah, that'd be the
anything.
safe way. It'd be the
Okay.
safe way.
Yeah. And then my second question is, in the real world, when we start going for publications, like you were just saying earlier, that usually you would just do like one-fold test training and testing, but I feel like for publications, they may want it to be more rigorous. So is K-fold cross-validation like the norm when it comes to trying to getting these into research, into journals?
So I kind of hinted at this when I was talking. Actually, K-fold cross-validation is less rigorous. It's
okay.
less rigorous because if you're reporting error on that, okay. If I train on a training set and I evaluate on a validation set, that validation set is physically independent of the training set. And so that's an unbiased estimate of the error. If I then average this over all K folds, you've introduced dependency across the folds in a very, very subtle way. It's not obvious how this works. Excuse me. And so like you're gonna get some number out, and like that leave one out cross validation number doesn't really mean, it's not very interpretable. I don't know how to interpret that number. I do know how to interpret a single fold. If you just do a single fold, that's very interpretable. But for practice, I get. But what I want you guys to really focus on here, though, is that like you really can do whatever you want with a training and validation set. This is really just to get a model out. Okay, you can contaminate the training and validation if you want, but you just have to be careful that like if you're choosing a model based on the validation number, that number doesn't mean anything if you're contaminating the training and validation. But like if you can do whatever you want to get some model out of
I can't see you writing. I don't. If you're writing something, I can't see it.
Well, it's minor. But yeah, if you're using the training validation set just to get a model out, that's fine. I don't really care. Because as long as you never touch the test set, when you evaluate FHAT on the test set, you'll get some number out. And that is the number that is independent, it's fine, it's great. The reason why you don't want to contaminate the training and validation set is really so that the number that you're getting on the validation set is actually a real predictor of how it's going to perform on the test set.
Yeah,
it's more of a check for yourself.
Yeah.
It's a check for yourself so that like when you go evaluate the test set, it's not a big surprise when the number comes out. Like you can, you should be able to predict what the test set's going to be, what that error is going to look like. And if it's not, then like it's okay. Like you can do whatever you want. You can really screw with the training and validation set, but like all that anyone really cares about is how you perform on the test set. And for publications, sadly, how much people trust your results, how rigorous you are, basically comes down to how trusted are you to have not looked at the test set to choose hyperparameters. And that has to do with reputation, sadly. And it can be very tricky. And all you can really say is like, we only looked at the test set once. And so like you can write that. And if you say that, then people have no other choice than to hopefully believe you and that you're doing good science. But that's the most rigorous way to do it. I don't care how you get some FHAT based on training validation. That's more for you. That's your sort of job. And then you're getting some FHAT out, and that all that people care about in terms of rigor is how that FHAT performs on a test set they only evaluated once on.
And one reason there's a big push for releasing the code and data sets you actually use to train a model and evaluate a model is that like if you're being sort of not nefarious. You know, in theory, people could find in your code or in the way you touch data some mistakes, like the ones Kevin was describing various points throughout class, that might say, hey, you're doing something suspicious here, right? And like, you should make sure that like this is not a problem / this is a problem. Like, I won't accept this paper until you fix this thing, right? On the other hand, like, you know, just because you show me some code that produces a model doesn't mean that that's actually how you got to that model, right? So it's not going to be sufficient to prove that you haven't touched the test set more than once, but it is some limited evidence that like there is some reasonable code that produced this model, and hopefully that code only touched the test set to give you the test numbers that you published in the paper.
Oh, thank you.
So there's a question here of like, so the idea of we only look at the test set once, what are all the different models we try on the test set? That's very much what I'm saying you should not be doing. You should not be trying lots of models on the test set. You should, as an individual researcher, you should be trying different models and evaluating on your validation set. And then of those different models that perform the best on the validation set, then you go and decide to publish that model. And right before publication, you evaluate on the test set once and report that number. That's how you should be doing this. And for comparing to other existing prior work, they should have also been doing that. And the fact that you saw how their model performed on the test set and now you're evaluating that same test set perhaps is a major problem. This is called sort of adaptive data analysis and can lead to overfitting and things like this. And this is like one of the most exciting, it's a very exciting area of research right now of like, are we really hurting ourselves by looking at this test set multiple times implicitly by you are considering a resonant model because someone else looked at a resonant model and it worked and they got a higher test error or a test accuracy. So now you're looking at a resonant model. That is implicitly through that information transfer, you looked at the test set in some way. And so this is theoretically a problem that the community is grappling with. And it's an active area of research. But the best, so all you can do is keep the best principles as an individual researcher and you'll be fine. But you should not be evaluating multiple models on the test set. So if you want keywords for this area, it's called either overfitting to the test set, adaptive data analysis is a big keyword here. Yeah, so big people in this area that have published a lot are Moritz Hart at Berkeley and Ludwig Schmidt as a postdoc at Berkeley as well. He actually just gave a talk 2 weeks ago here, or last week.
Also some folks from the differential privacy space, right? So Cynthia Dwork and Aaron Roth, amongst others.
Mm-hmm. Yeah, privacy is a very close related issue to this. It's very interesting. We're probably not gonna get there in this class though. Okay, can I do lasso in 5 minutes? Let's see. We'll just stop early, or if I don't, or we won't get through all the slides. So a moment ago we were just talking about selecting variables for having, we have started with 10,000 dimensions. We want 50 dimensions. Big reason why you'd want to do this. When we call a vector sparse, a vector W is sparse if it has many non-zeros. Sorry, many zeros. A vector is sparse is if many of its components are 0 and only a few have non-zero. And so it's just basically saying that if the size of W is 100 billion, maybe only like a few of those entries are actually non-zero. And so you can compute, oh my gosh. All right, I am never screen sharing again. This is terrible. And so if you had 100 billion variables, then to compute this inner product, only a very small number of these entries of these vectors are non-zero, and so this computing this sum is like very, very easy. It's very computationally efficient. You only need to store the non-zeros. But the big thing is actually for interpretability. So like for housing price, there could be tons and tons of features, like the number of bathrooms, heating, microwaves, I don't know, jetted tub. What's a jetted tub? And we have all these features, and now we want to figure out, like, okay, we're going to learn some predictor, and I'll put numbers on all of these things, basically. I'll learn some W, put a weight on each one of these features. But like the whole linear combination of 100 different variables is not very interpretable. Maybe you can pick out just like 3 or 4 that is just as good of a predictor, but maybe more interpretable. And so if you just wanted to find, say, like the best 5 non-zero components, so you're looking at all 100 features, and you're just trying to find a predictor that is at most 5 of these, you want to find the best predictor among that. The problem here is 100 choose 5. If you were to look at all possible 5 subsets, is a big number, like 100 to the 5, so 100,000 at least, and that's just computationally infeasible for a lot of problems. And so people do heuristics, like adding one at a time. Train with one, find the single best feature, add it to your set, and then train all, just add one more at a time. So that is now going to be one you're using, and then search over all 99, and then pick the best one that increases the accuracy the most, and then add that to your set, and then add a third one, so on and so on. That's forward stepwise regression. You could also do backward. Basically, you train all 100, and then you remove the coefficient that's smallest, or you search over all 100, taking one out, and which one that you take out reduce the error the least. So like which one really didn't have much of an effect, and you remove them that way. So you've turned the search into more of a linear complexity than this exponential potentially. And then you can also combine these forward and backward steps in this sequence. Lots of heuristics in this way. Sometimes you can prove things about this. Most of the time you can't. But another way of doing this is thinking about recalling ridge regression. What ridge regression did was it was biasing you towards solutions that were otherwise you were indifferent towards. Okay, so it was saying, look, all things being equal, I prefer a solution with a small L2 norm. And can we have the same sort of strategy? This is basically killing off small coefficients. That's the effect it has. It shrinks the coefficients towards small. So maybe a very natural idea, for different lambda, the coefficients of W change over time. A bigger lambda creates smaller W's. So a reasonable idea is to just sort of threshold your coefficients, right? Train some ridge regression estimator with some lambda, and then just choose some threshold here and kill all coefficients below this threshold in absolute value. That seems reasonable, and it might work, but something really strange happens here. So if we just look at 2 features, like number of bathrooms and number of showers, these are obviously correlated, perhaps very, very correlated. And so if I were to, each of these features is below the threshold right now. But if I were to take one out, if I were to kill showers, then what's going to happen is the number of bathrooms coefficient is going to increase, because this is a linear model. Together, both of them were under the threshold, but they're completely correlated. So that I could have used either one, or I could put all the weight on one and 0 the weight on the other one, or half and half, which is the case here. So if I take that one out, now that coefficient is above it. But there's no telling what would have been preferred here and what would not have been preferred. Ridge regression is really just trying to minimize the L2 norm and minimize these coefficients. So it's sort of the wrong regularization. And so next time, we'll talk about a different kind of regularizer called lasso, which instead of the L2 norm, we're going to add the L1 norm, and it looks more spiky. And this is going to essentially be encouraging this kind of sparsity that we're looking for. And so we're going to talk about this next time. and how this encourages sparse solutions. And then we'll show that this is a convex objective, even though it's not closed form. And then we'll get into other objectives that are convex, and then we'll have a big discussion about that. Okay. So that's it for today. And I'll take questions for the next 10 or so minutes. Sahil?
You were saying for the interpretability, you either like start from a simple model and add features if they're important. Like, I understand the backward way, like you train on all the features and then find that some of the coefficients are low and then remove them. But how do you do the forward step? Like, how do you find features which are important, which you have not even trained on?
Right. So how that works is to get the first one, you're going to train a predictor just using one coefficient. So if you have D features, you're going to train D different predictors, just using each feature individually. And then you're going to use the one that predicts the best. Whichever of those D predictors predict the best that are just using a single feature, you're going to choose that dimension, and you're going to add that to a set. Okay. Now you've got one feature. So you had to train D models just to pick one. Now that you've picked that one feature, you're now going to repeat this process of you're going to use that one feature, but now you're going to loop over all D-1 features and add that one to that initial one that you added to your set and see how all those 2Ys predictors act. So that's going to be 99 models. And then you're going to predict the one that has the best predictive performance. And now you're going to add that to your set. So you have two features, and you'll add one at a time like that. And so you're not just looking at small coefficients, you're actually training a new model every time to figure out which additional feature increased the performance the most. And the same thing with the backward, you start with all 100, and then you look at all models that have D-1, that are trained on D-1 features, and whichever one performed whichever one didn't change the model the most, you remove that one.
Okay, thank you.
Yep.
Hi, teacher.
Yes.
I have a question on can you scroll back to the previous slides about the recap slide about the cross validation, like split the train set into train and validation. It's 12, page 12.
This one?
Yeah, this one. So when we are splitting the training set into like the validation set and train set, we are only using the train set to train the model. And sometimes we do some pre-processing the data, like we demean or we standardizing the data. Will we do the same procedures for the validation set or not?
Great question. Yes. So these pre-processing steps, you'd have a mu1 and a sigma1 for these pre-processing steps. You'd have a mu2, sigma2, mu3, sigma3 that are just being trained on these individual training sets. And then you're going to apply those same standardization steps to the validation set.
Okay, so we do not standardize, we do not pre-process it.
Yeah, you don't standardize the entire train.
Okay.
Because if you did that, again, then when you looked at these folds, your validation would have bled into this training set. And so the number that you'd get when you evaluated on the validation set would not be unbiased because the validation bled into the train. And so if you're picking numbers based on this, they could be misleading. And so basically, it's sort of like it's this Russian doll sort of thing, where like you start with a big data set, you split up in a train and a test. Now within each train, within the train, you then split that further, but you always use best practices where any pre-processing or standardization or anything is done on that smaller training set, and then you do that once you've chosen that parameterization, like that mean and variance to standardize data from, you apply that to the validation set.
Okay. Okay. One more thing follow up is that we were also told that the error on the validation set is a biased estimator. Can you give any tutorials or explanations why it's a biased estimator?
It's a biased estimator simply because the validation set has bled into the training set. They are dependent in some way.
Okay. We cannot.
That's
okay. We cannot.
That's simply it. If you want to train something on this smaller training set and evaluate it on the validation set, you want that number to mean something, then the validation set could not have affected how you trained that verse model. And that could be as much as computing a mean and variance, something as small as that. And so if we go back to this sort of gold standard example, note, we are not ever demeaning of this train and validation. We choose a training set. So we choose a train, validation, test. And then those are the indices, and we allocate our training and our validation. And note, we do not demean the training set. We don't do that. What we do is this is doing a cross-validation step. This is just picking the first D features. So I've somehow ranked my features. I don't know how. This is an example. So I know I'm only going to pick the first D. They're sorted somehow. And I want to figure out the D that is the best D features. So what I do is I'm going to pass my training of just using the first D features into this function fit, and only there do I then compute the mean and d-mean, that smaller validation set, and then I evaluate on the validation set using a predict function, and then I get my error, and then I pick the D best, the value of D that I'm cross-validating over that has the smallest error. And only then do I then compute. In this case, as the question before, I do combine the training and the validation set into one big data set, X total, and then I fit on that.
Okay.
But this is critical. You really want it. That's why it's so best practice to define like a fit function that just takes a training set as if it was a training set and a predict function, so you don't contaminate the validation set with the training set.
Okay. Thank you so much. Yeah, thanks.
Chetan, I think you're next.
Yeah, so I had a question about standardization just on the training set. So about like a couple years ago at UW, I took a machine learning class, and I had asked this question about normalization. And in my notes from this class, they were saying that it's okay to perform normalization on the whole data set before cross-validation, only if you're performing it on the data set, not considering the Y outcome or labels. Is there ever a situation where that makes sense? Or
that's almost true. So you can perform pre-processing if it doesn't touch the data set at all. Like, for instance, if I were just to know the way that the data was collected, that it's off, I have to, everything was just added 1 to some dimension, I could subtract that 1 off because it had nothing to do with data. You can only sort of like just before you see anything, do some sort of pre-processing on the entire training set, precisely because you didn't look at data to make that decision. That was the decision that you made based on other prior domain knowledge. And so that is totally okay, but it's not true that, I didn't look at the Ys. No, like if you look at the X's, that's enough to bias you. Knowing the features is a bleed of information. It's not just the y's. So
Okay.
you cannot look at data at all to make these pre-processing decisions. I mean, like, it depends on the particular domain. It sometimes may be okay, because like sometimes you know the x's beforehand, because like, I don't know, sometimes you know the x's beforehand, and like it's not looking at that data doesn't give you any additional information about your prediction problem, which is, can sometimes happen. But oftentimes the x's do contain information, and this can be a major actually problem that when we talk about fairness later in the course, we'll see that an enormous amount of information is encoded in those features, and just looking at them can have a major impact on what you do and how you act with that data.
Yeah, okay. Yeah, that makes sense. Thank you.
Yeah. And a lot of what I'm saying may contrast with things that you've heard before, or especially if you're in a lab doing research, what I'm telling you may contrast with what they're doing in practice, mostly because they are not following best practices.
Right, yeah.
They are contaminating the test set. And this is just something that happens because people are sloppy. I am teaching you best practices and what you should be doing. Any deviation from these strict standards should be done with extreme caution, and you have to know what you're doing. And to do so unwisely or without understanding the consequences is extremely dangerous.
Makes sense.
Salen? Or
oh, Caitlin.
Kaylin, sorry.
So we said earlier that the optimal weights in ridge regression depends on the size of the data set. And I was just wondering how does that make sense if like you get, you pick a lambda parameter for that training set, and how would that, if how can you use that model to on scene data if it depended on the size of the training set?
So the parameter, the optimal value of lambda depended on the size of the training set.
Right.
And so that can happen very frequently. So when we went through that analysis of ridge regression, where we did the model and bias, the bias and variance trade-off explicitly for that very special example, you saw that the value of lambda that was optimal depended on n, the number of training steps.
Yeah.
And so in that case, if you think you're in that kind of situation, what you would want to do is basically, after you have, so after you've picked your, you use this 80% to train and choose, you evaluate in the 10% to get some lambda hat. And this is like, we'll call this 80 because like it was trained using the 80%. And now, if we then use this lambda hat that was evaluated on the 80%, but then lambda hat, comes from cross value CV on F hat of 80, let's say, of lambda, meaning it's trained.
Could you refresh the slides? We cannot see what you're writing. Thank you.
Thank you. Sorry, guys. I'm done with mirroring. So if we choose some lambda hat 80 based on the 80%, so I trained F hat 80. So this is meaning I'm just looking at the first 80 data points. Right? I'm looking at 80% of the data. And I'm choosing this optimal value of lambda here based on my validation set. And then I choose, so I do that, and I get a lambda hat 80. Now this lambda hat is optimal for a data set of size 80. I mean, at least in this, you'd hope that when it generalizes, it's really tuned for a data set of size 80.